it's a real pleasure to be a part of this birthday celebration of Professor T.V. Ramakrishnan. Okay, so the topic of my talk today is dynamics of ultracold bosons in optical lattice. So this is a work that has been done with Krishnendu Sengupta, who has been a student of Maciej Lewenstein in Barcelona when he was visiting me, and also with David Pecker, who is currently a postdoc at Caltech. So here is a brief overview. So first I would like to motivate why we study dynamics in these systems. Then with an introduction to ultracold bosons, talk about the Boson model, and that's one of the models in which I'm going to study this dynamics in. Then talk about bosons in a quote-unquote electric field, effective electric field that is generated in this optical lattice system for the neutral bosons, and talk about theory and experiments in there, and subsequently go on to talk about the dynamics in the system, and this will be followed by conclusion. So the question is, why do you want to study dynamics in a closed quantum system where in reality, at least till a few years back, such systems never exist in the laboratory? And the answer to that is that it has a deep relation with cold atoms, and there are experimental systems now in the field atoms which are very, very close to perfect realization of closed effectively zero temperature quantum systems. And this also includes ion traps. And the other interesting thing about these systems is that they act as so-called quantum emulators, and they can be used to sort of emulate models which we have studied in the context of condensed matter physics for a very long time. And this gives us a wonderful opportunity to study dynamics of these models, which was not thought to be so important till recently because of other issues with standard experimental system. So what are the conceptual issues with non-equilibrium dynamics? The first thing that comes to mind is basically universality in out-of-equilibrium systems. So in equilibrium systems, we know that universality is a way of understanding why simple models can often describe properties of very complicated real-life systems. And it basically tells you which couplings in a very complicated systems become irrelevant at low energy scales and which you need to keep. However, and that's a well understood phenomenon now, but when you go to out of equilibrium and study dynamics, till then there is no general answer as to whether such universality holds. So that's one of the questions that's there in the community. The second thing has to do with the nature of the steady state at long times after you have realized the dynamic protocol. So you keep the system and then let it evolve for a long time, and the question is, what's the nature of the steady state at long times? In particular, whether these systems being closed effective zero temperature system has effective thermal state as the steady state. So the other interesting things are short-time dynamics, such as whether by studying the short-term dynamic properties of the system before it reaches a steady state, you could see some signatures of quantum criticality if you were talking about the system near a quantum critical point. One needs to understand defect productions in quantum systems, starting from the very early work of Kibel and Zurek. I mean, this is an issue which has led to many different scaling laws and beautiful realizations of those. The other thing which has come up recently, and which of course I am not going to touch about at all, is study of dynamics in field theories in the strongly coupled regime. And so we know that such field theories, some types of those field theories are related to gravity via this ADS-CFT correspondence. It would be interesting to see that if we have a way of studying dynamics in these field theories, what it does to the theories of gravity and vice versa. Okay. So this is sort of my motivation, and so let me go to more mundane things like ultracold bosons in an optical lattice. And here is a brief introduction. So what do? You take a bunch of cold atoms, and this is a theorist's way of understanding experiments, but pardon me for that. So you cool them in a trap, and once they are there, you apply counter-propagating laser, which forms a standing wave of light. Now these atoms are neutral, but they feel a potential because of their polarizability, and that depends on the intensity of the applied lasers. And so if you choose your frequencies and other things, right, which I cannot do but the experimentalists can, you generate a potential contour for these atoms, and the most easy to achieve potential contour is that of a square lattice or a cubic lattice in 3D. So for a deep enough potential, so these atoms now have two contributions. T, the hopping between the lattice can be made small compared to U. Okay. So essentially we are going to look at a regime where we don't need to invoke higher bands, okay, not even in dynamics. So here is the experiment which started it sort of. So what happens is basically in this experiment which was in Emmanuel's blog group, they took this system and they ramped up the lattice potential to some Vmax or V0. Sorry about the Vmax is basically V0. And then they let the system equilibrate for some time, drop both the trap and the lattice, and measure the position distribution of the bosons which are flying out because you have dropped the trap. Now once you do that, what happens is that because it's a free flight, the position distribution of the bosons when you image them is basically the momentum distribution of the bosons inside the trap, because it's all in the initial conditions. Okay. So and when your trap is so when your lattice depth is really small, you see that all the bosons are at k equal to 0, whereas when it's large, they are at large k. So they are all basically evenly distributed, they are completely random. So this means that here they are localized in momentum space, here they are completely delocalized in momentum space, and in between somewhere the central peak disappears. So this was interpreted as having a quantum phase transition from a superfluid to an insulating state. So how do we treat the superfluid insulator transition in a Bose-Hubbard model? So very preliminary analysis. So imagine that you are in the atomic limit. So you just have the on-site energy and the chemical interaction energy and the chemical potential. So this, as one can easily see, this has stable ground state, which is a Mott insulator. And we are going to take mu to be between 0 and U, where there is one boson per site. Now, just think of adding a particle to this state. So you pay up an interaction energy which is U minus mu, but now this boson can keep on hopping and it can lower its energy by that, and that energy lowering is 2ZT, where Z is the coordination number. For hypercubic lattice in D dimension, it's 2 times D. For other type of lattice, it's a different number. So this gives you an estimate of when the Mott state is going to be destabilized if you are so when the Mott state is going to be destabilized if you are adding a particle. Similarly, that's when this excitation energy vanishes. Okay. Similarly, you can remove a particle from the Mott state, and this is going to give you an estimate of when this holes we are hopping is going to destabilize the Mott state, and you can get a phase diagram from this. The minimum of this TCP and TCH is going to determine your Mott lobe. So, of course, this is a very simple-minded analysis, and one can go much beyond this simple feature. So, there are several theories. So, for example, this theory could be generalized to take into account higher order energy corrections, which has been done by Friedrichs and Monian somewhere in the 90s, and they produce a really accurate phase diagram. So mean field theory, which was first done by Matthew Fisher in '89, and then a very beautiful paper by TVR and his collaborators in Bangalore, which detailed out this mean field theory. There have been extensive quantum Monte Carlo studies in this system because these are bosonic systems where you do not have the sign problem, and there are some very nice data for 2D by Nandini and Kraut, and now by Bella and her collaborators for 3D systems. So we really know where the phase diagram, what the values, numerical values of the critical point is. And all of this predicts a quantum phase transition with dynamical critical exponent 2, except at the tip of the lobe where the additional particle hole symmetry changes your universality to Z equal to 1. However, in all these methods, except for the mean field theory, there is no method for studying dynamics beyond the, so no method for studying dynamics. So what we would like to have is a method for doing that beyond mean field theory. Okay, and so that's the motivation for what we started. This is a projection operator approach. So the basic point about this approach is that you distinguish between the hopping processes. So imagine that you have a Mott state and you consider hopping where a boson goes from site here to there. This costs an energy E. Okay. Clearly, this state has a higher energy compared to this because of the interaction energy cost. And near the critical regime or in the Mott phase, what happens is that this is a high energy process. On the other hand, if you are considering a different state, like one in which there is a hole, this hole can freely hop, and this is not a high energy process. So the way to sort of take care of this within a Hamiltonian formulation is to define a projection operator, which is, so this operator lives on a link, and this operator projects it to the Mott ground state, and it gives you 1 if the occupation of the left and the right side of the link is just the Mott ground state occupation, which is M bar, which I am going to take as 1 in the rest of the talk, or it annihilates the state. Otherwise, if they are not 1, it annihilates the state. So now, using this projection operator, I can divide the hopping into classes B and C. One of them is this PL, TL, and TLPL, T being the hopping thing. The other thing is just what is left out. This PL perpendicular is the short form for 1 minus PL. Okay. So I'm just writing the hopping in this way. And now you realize that near the so what you realize is that those terms, this PL, TL, and the others, those are the ones which are responsible for the high energy processes near the critical point as well as in the Mott phase. So what you do is to design a canonical transformation which would systematically eliminate those terms from your Hamiltonian. And that's a well-known technology. It has been done in a lot of contexts, and once you do this, you get this effective Hamiltonian. So now to compute the energy, first let's get to the equilibrium phase diagram and see what this method does. To get the energy, you know that, so we know that the energy is just the expectation value of the Hamiltonian. Now with the transformation, I can write this as that, and if I am keeping all of this to order j square over u, which I am doing, the difference is going to be of the order j cube over u square. Okay. And this psi prime is the transform state, which is exponential IS. S is the transformation operator, and in what follows, I'm going to take this psi prime, that is the transform ground state, as the Gartz-Wheeler mean field state. This doesn't mean that the real wave function is Gartz-Wheeler mean field. It has spatial correlation through this wave function S. Yeah.
Explain physically the one over u term. There are too many of them.
Oh yes, so let me just say this. So these are the t square over u corrections over the Mott state, that's there. And these are the terms which comes because you have so to second order, it's possible for the boson to hop 2 sides and go to the next link as well. So you divide this into these classes, and just those are the terms.
In the case of Mott insulator, it gets super exchange.
Yeah. Here it's a little easier, I would say, because the spin thing is not there, so.
There are too many.
Well, okay. So I have to keep what I get. So apparently here is the phase diagram, which is obtained by minimizing this energy that you have. And apparently in 3 dimension, this method gives you a very close analog to quantum Monte Carlo, which is a good thing. In 2 dimension, it's not so accurate, but that's understandable because in here we are sort of adding fluctuations over some mean field, and that becomes better as the z or the number of nearest neighbors increases. Okay, and so we saw that that's actually the case. But now let me move to the main topic, which is the dynamics. So apparently this method, the beauty of this method is that it allows you to study this non-equilibrium dynamics at the same footing, because now what you can say that suppose I invoke a protocol for studying dynamics where I make my hopping time dependent. Okay, so this j becomes now j of t, which goes from some value, initial value ji to some final value jf linearly in time. The point is that we can repeat this procedure just by making this as a time dependent transformation. So instead of solving this the full Schrodinger equation, which is complicated, to order j square over u square, I can solve this equation, which is the canonical transformed version of this. And this procedure is going to be okay as long as j of t over u is small at each time instant. Okay, then I can successfully, I can reliably ignore higher orders in j. And this gives me a bunch of equation in terms of this Gutzwiller coefficient, which I just showed you. Without getting into the details, I can just solve this numerically, and I see what I get for the dynamics. Okay, so that's the idea. So apparently one thing that we measured is basically the wave function overlap, which is a thing which tells you that so suppose you start from a given state and you go to the final state after the dynamics, how much overlap do you have with the final ground state? And that 1 minus Mott square of that is basically your number of excitations. And we found that it has a plateau-like behavior at large u, which is a little surprising because here you are passing, in this protocol, you are passing from the superfluid to the Mott insulator phase, so you are going through a quantum critical point, and you would expect that there are some scaling laws, okay? Because that's the standard Kibble-Zurek argument, that when you go from one phase to the other through a critical point, you should have this. And the reason why it doesn't happen here is that even for this tau u to be of the order 30 or so, there is absence of critical scaling because it's too fast. The reason is that imagine that these bosons are localized at a given lattice site, and you are going from the Mott phase to the superfluid state. So the amount of time that it spends during the dynamics near the quantum critical point should be long enough so that the system can access the k equal to 0 modes. So it should have enough time to delocalize. And some simple calculation based on realistic parameters, at least I'm going to show you the experiment right afterwards, tells you that that never happens. If it did, this theory is not going to give you a proper description of the defect production, because here correlations are added order by order in J, the special correlations, and getting k equal to 0 physics out of this is very difficult. But in this context, and I'm going to show you the experimental this thing, even for the current experiment, this is okay. We also looked at the order parameter oscillations and how other stuff behaves, and so here is how the order parameter. So in this we took this system from the critical point to a superfluid phase with still j over u being small, and looked at the subsequent dynamics of the order parameter. So if you are really near the critical point, this dynamics is of a single peak. That frequency is basically the particle or whole creation frequency, and since we are at the tip of the Mott lobe, these two are actually the same. So we have just one frequency. However, if you go slightly deeper into the superfluid phase, there are more frequencies which are involved, the dynamics get complicated. So no surprise there. What we are also able to calculate is this C of t, which is the order parameter correlation function. This is beyond mean field, because mean field is just going to give you 0 for this, and it seems that there is quite a bit of correlation beyond mean field here. Yeah. I'm sorry, no, this is for very fast dynamics. Yeah, so this is Quain's dynamics that you let the system evolve. Okay, so that's it. Okay, so here is an experiment in the group of Marcus Greiner at Harvard. So they looked at this 2D BEC confined trap in the presence of an optical lattice, and they can do this amazing single-site imaging, which I'm not going to get into the details of. But the point is, they also measured this wave function overlap in some sense, and you see here that this also reaches a plateau. And the basic reason for this is that in their experiment, they have a JC which is of the order of 68 milliseconds, and their ramp time goes up to 20 milliseconds. And you can estimate that because of the system size, it takes of the order of 10 times that is of the order of 700 milliseconds for a boson to delocalize. And they are really in the fast regime as far as delocalization is concerned, and so they do get this plateau and not a scaling law, which is not so surprising. Okay. So this is about Bose-Hubbard model. And okay, so just Yes, so the point is that, in this what we have done is to look at a uniform homogeneous system, right? But real life is not homogeneous, as you know very well. So there are some interesting spatial patterns as to how the defects form. And that is something beyond the theory now, but I believe it would be interesting to see, to keep all the inhomogeneity and do this, and one can do this within some approximation. I haven't got to that yet. So that's the, okay, so next I'm going to come to the, so just one more comment. Not only you can do linear quench, you can do basically any quench, and we looked at nonlinear ramps also. And nothing much changes. You always see that at large tau, that is for slow quenches, you get this plateau stuff. And so there is this initial non-monotonic, there is this initial slope which has a non-monotonic dependence on tau, and that's pretty much it. So now I'm going to talk about sort of a different model where bosons are kept in an electric field. So this is again the Bose-Hubbard model, but now it's deep inside a Mott insulating phase. Okay? So U is a large energy scale. But now what you do is to sort of tilt these bosons. Now this can be done in two ways. One is basically if you take the trap and shift the center of the trap, which would mean that if you had a harmonic trap, now we would have a shifted harmonic oscillator. And the shifted harmonic oscillator is like a linear potential, which is like an electric field for these bosons. Okay? The other way that, experimentalists are always more clever. So the way they do it is that they take spinor bosons with spin 1, and they apply a Zeeman field gradient, okay, which does the same thing. So I'm just going to take one or the other. So here is the tilted lattice, and this is some very old work that we did during my postdoc days with Subir and Steve at Yale. Subir was still at Yale, so these were the old days. So essentially, in this tilted, so this is the parent Mott state. Okay, so this is the Mott state where the electric field has been applied. Okay, and this is its Hamiltonian. And the regime in which we are going to work is that both the electric field and the potential, so the on-site interaction is large compared to the hopping, because it's in a Mott state, the hopping is small, and the difference between U and E. Okay. So these two can be arbitrarily small. So what you would like to see described is basically the low energy physics of this system, and to do that we want to first understand the subspace of states which is resonantly coupled to the Mott insulator, and so let's see how to do that. So in the Bose-Hubbard model, I told you that one way to destabilize this Mott phase is to add particle samples. So we could try the same thing here. So we could either add a particle or a hole, but the point is that if you do so, now the particle or the hole that you have added, it doesn't only have a hopping term, but it also has an electric field term. And this is the one-year stuck problem in a 1D lattice. And you know the exact eigenvalues and the eigenvectors, and these are very well localized. So this particle or hole excitation do not belong to the category of low energy resonant subspace, because you pay some energy to add them, and then it doesn't gain enough energy by delocalizing. So it's not going to destabilize the state. What does destabilize the state are these dipoles. So if a boson hops from one state out here to another state, to the next site, what happens is that this costs an energy U minus E. So when U minus E is basically small, or when they are exactly equal, these are resonantly coupled to the parent Mott state. And by this token, one can also see that, so this is equivalent to formation of a dipole, which is a bound state of a hole and an electron. And the reason this is a bound state is that if the boson makes another hop, it costs an energy E minus 2E, which is not a part of the low energy subspace. Okay. So this neutral dipole state, so the idea is to make a dipole model out of this. Okay. And that dipole model is basically that. So you pay an energy cost U minus E to create a dipole, and then these dipoles, because of the hopping term, can be spontaneously formed or destroyed. Okay. So, and there is a constant, that is the number of dipoles per site is not more than 1. Okay, it's either 0 or 1, and that two dipoles cannot form at neighboring sites. So this one can show is again not a low energy process. So we want to determine the phase diagram of this, and this is reasonably easy. Okay. So what you want to do is that you take a weak electric, so if the electric field is weak, the ground state is a dipole vacuum, because there is no reason, because U minus E is a large positive number, so it doesn't form, and then you can estimate the low energy excitations over that. But, and when, how much time do I? Okay, so perfect. 20 minutes, so I think I'm going to finish early. So, okay, so let me explain this a little bit more. Okay, so then you could talk about finding the effective excitations over these dipoles. So essentially, you have a energy creation, and then there is a band. And this lowest energy excitations are single band of dipole excitations. Now, as you approach this U minus E to 0, so when the electric field is increased and it approaches U, you see that this excitation softens, they become gapless, and this is a precursor of the of what we are going to see as a Ising density wave with period 2. I'm going to come to that, but it's certainly a precursor of destabilizing the phase. Okay, so you can sort of get an idea that there is a critical point sitting there, and then you could also estimate the higher excited state, which will be some multi-particle continuum. It's a very reminiscent of the paramagnetic phase of the Ising model, and there is some reason for that. So. Okay, so now let's say what happens in the strong electric field case. So your E is very large compared to U. Okay, so U minus E is a large negative number. So if that happens, then because of the constraint of not having two dipoles on a given consecutive sites, you would have two degenerate ground states. Because a ground state will have maximum number of dipoles, but these dipoles can form either at odd links, or rather, the holes of the dipole can be at odd sites, or they can be at even sites. Okay, so there is this odd-even effect, and this reminds you of the Z2 symmetry breaking of an Ising model in the ground state. So the first excited state consists of domain whirls, and it's very similar to Ising model in a transverse field. So this sort of motivated us to study this using exact diagonalization. This was perfect because of two things. One is that it's a one-dimensional system, so exact diagonalization is the method of choice, and in some sense it's better than Ising because I have more constraints which takes out more states from the Hilbert space, so I can study larger systems. So we did this, and it's not at all surprising that we found an Ising transition here, and this transition occurs at E minus U to be equal to something close to 2W, and that extra kinetic energy is needed because you need that, so this extra electric field is needed because you need to freeze down the kinetic energy of the bosons, and that's where the transition takes place. So the reason I talked about this model is that this is one of those lucky candidates which got experimentally realized very recently. This was again done at Griner's group, and this was a Nature paper in 2010. So what they did is to realize this dipole model, and they used that gradient of Zeeman field, and apparently they converted into a spin model and mentioned that this was the first experimental realization of an effective Ising model. But this is the spin dipole operator dictionary. So if you know the dipole operators, you know your spins, and this J was set to infinity in our model, but that's of course a constant of the order of U, or the large energy scale in the problem. And then we have a longitudinal field and a transverse field which corresponds to the dipole hopping and the dipole creation terms. So apparently they have seen, so they can do this single site readout, can see so what they can measure is the parity of boson occupation on a given site. And so when you have a dipole vacuum, that is one boson per site out here, they see odd occupation, whereas by tilting by increasing the electric field or generating additional tilt, what they can see is basically even occupation. Okay. So this odd even, and they have clearly seen, so they have done this in the phase diagram. Okay. So basically, I think it was crossed somewhere. It was crossed somewhere here. I don't remember the exact numbers in the paper, but for some finite value of Hz and Hx actually. So again, coming back to dynamics, this now gives us an ample opportunity to study dynamics across the quantum critical point. So right after this paper that we wrote with Subir, we also did some work on in a separate paper on this quench dynamics in this system across the critical point. So here what we could do is to tune the electric field from initial value EI to EF instantaneously and go across the transition. And we wanted to look at the order parameter, and in particular, if we plot the time average value of this order parameter, the function of time, it has a peak at very near the quantum critical point, not exactly at the critical point. And the reason is that this order parameter is a product of the overlap of the new wave function with the old ground state, and also the expectation value of the order parameter between these states. And this product is small if you are either very near the initial state or too far away from it. In between, near the critical point, this attains a maximum. Okay. So that's why this peak is here. And this is something which we'd like to see in experiments because they can now really do it. More recently, and this is going to be the last thing I'm going to talk about, so we studied dynamics with a finite rate. Okay, so that's when we took this electric field and varied it linearly as a function of time, and we calculated a bunch of quantities. And most of these calculations are done by by studying dynamics together with finite sized diagonalization. So the thing that we wanted to go for is is this finite size scaling laws. Okay. So let me take 2 minutes to give a brief introduction to this. So if you have a thermodynamic system and you are doing this out of equilibrium stuff, and you are passing through a quantum phase transition, what you find is that let's say your defect density, which is this F, would scale according to some fixed power. This V is some dimensionless rate, and it scales according to d mu by z mu plus 1, where z is the dynamical critical exponent of the phase transition, and mu is the correlation length exponent, d is the dimensionality. Now this is for thermodynamic systems. For finite size system, there are additional functions, combinations of V and L. So the idea is that if your velocity or the rate, if your rate at which you are going through this quantum phase transition is small, then you are going to not see a Kibble-Zurek behavior because of this thing. You are going to see instead of so for the current system, D is 1, Z and mu are also 1. So you expect a rate dependence of this, which is somewhat like V, but you are going to see a V squared dependence because of these scaling functions. So the interesting thing for the experimentalist would be to tell them that for what value of V they are going to see this Kibble-Zurek scaling, and that's the answer that we wanted to get. So the thing that I want to emphasize here is that it's well known, at least in the context of the scaling laws, that scaling laws always hold for slow dynamics. However, if you are studying finite size system, it really holds at intermediate dynamics and not at slow dynamics. If you do slow enough, what you are going to find is that you get a gap in your energy spectrum because of finite system size, and that's going to give you some completely different behavior. It turns out to be V square if you have a finite system size and you are doing a finite time dynamics. So apparently this is our result. So we find that there is some region of V, okay, in some dimensionless unit, never mind what that is, where you see this scaling, and there is all these different system sizes that we went. And please don't get scared by these numbers. These are not done always with finite size diagonalization. We really cannot do finite size diagonalization beyond L equal to 16. The rest of this is this TDMRG procedure, which some very numerical colleagues at Princeton did. But overall, the result is that there is a large regime where you could see this finite size version of the Kibble-Zurek law. Now, Kibble-Zurek law has been proposed in different contexts in many different systems, but in non-integrable quantum systems, till date, there is no experimental verification of this law, and we really hope that they are going to be able to do this. We could also measure other quantities which is relevant, sort of predict other quantities which would be relevant experimentally. One of them is this dipole dynamics, where we would like to see what the density of dipoles are, after we ramp them. And the other thing is the dipole-dipole correlation function, which can also be calculated, and they have pretty standard behavior which you would expect from the model. If you are doing this with a very slow rate, you are going to see oscillations, which is basically a signature of the signature of this Ising order parameter. Because in this, you are going from the paramagnetic to the ordered phase, and if you do slow enough, you are going to see basically the ground state correlation function. But as you increase your speed, you are going to not probe the ground state, and this oscillation sort of goes away, which tells you that you have lost the ground state order. So I think I'm finishing. Well, I'm done actually. So let me just conclude. So the study of dynamics in closed quantum system really started out as theoretical fancy of studying critical behavior in model systems. But now with these ultra-cold atom systems, I think we can go to the next step and see how they manifest themselves in non-integrable quantum systems. And these are two sort of models which has a chance of being experimentally realized. One of them, there is something which has been done. The other, the equilibrium part has been studied, but I'm very hopeful that they would be able to do dynamics. There are many more such models, and there are many more theoretical studies to do in context of different models in ultra-cold systems, and I hope that it's going to be very exciting in coming days. And thank you for your attention.
Comment is that there are absolutely no reason to believe that index Z is integer, 1, 2, 3, and so on. It can be arbitrary number, and it is arbitrary number in reality. Yes. So question is, just for me to have Z equal 1 is very unnatural, because what you are saying is that your dynamics is extremely fast. It is corresponding just to sound waves. So what is 1? It is just omega is equal K. So what does it mean? Just what for system is looking for the quantum phase point in order to have such a fast dynamics? Well, do you have any real indication?
Sorry. So you are talking about the boson model? The Bose-Hubbard model, or
whatever. The Z1 means that you have linear relation between frequency and momentum.
That's true.
So which means that your dynamics in the critical point is like sound waves.
Yes.
What for system is looking for the critical point in order to have such a fast dynamics? Do you have any
it's not in the fast dynamics actually. So the scaling laws that I talked about, they hold when the rate is slow compared to other scales in the problem. They don't hold for fast dynamics through the critical point.
Then why do you say that it is 1? If you see that it is slow, what kind of arguments, what kind of indication of this dynamics you have?
No, so the point is that, so you could take any Z that you want, and basically if you go through this dynamics calculation, you would find that there is a specific exponent with which the defect density scales as a function of rate. Z is a part of that exponent. It's really, that exponent is d nu by Z nu plus 1. Okay. Now what this Z is, this is not a self-consistent calculation of Z. Typically what people do, at least in this Kibble-Zurek kind of argument, is to take the equilibrium value of Z, which they take to be an integer, or it could be anything. I don't know, typically for, let's say, an Ising model, if you take this, it's going to be 1. And then you just see whether the defect production rate, the number of defects, they scale according to this power, if you put this. And usually it does. Okay. I'm not making the claim that if I take into account self-consistently the dynamics process, Z is going to be just the equilibrium Z. However, if you are doing this really slow, when you are going through the critical point, probably the deviation is not going to be significant. That's all I am saying. I'm not sure if this answers the question, but that's what I...
So Krishnendu, this reminds me of a familiar problem of having a lot of conductors, finite sized conductors embedded in a dielectric. And you have a U, you have an electric field, and you have some kind of dielectric breakdown when the electric field is too big.
Yes.
So, and your dipoles are essentially charging of the capacitors when the current is not really flowing.
Yeah, except, can I just add one thing? That the electric breakdown here is almost impossible, because so to have this electric breakdown, you need higher states in the same well, right? I mean,
You just need to populate the upper Hubbard band. That's right? That's it?
No, actually here to have the electric breakdown, you need to sort of go to the next single particle state, which is way up there. So the electric breakdown time for this problem often happens to be larger than the system lifetime. So think of just a model where you just have a band insulator and you have applied an electric field out there. You really need the upper band out there, right? You need to populate that to have the electric breakdown. Here that problem is, that is really in a very long time scale. You cannot stabilize the system till that. But beyond that, if you take a single band model, yes, these dipoles are like sort of charging the...
Yeah, because your U order E just indicates to me a current should flow at that point.
Yes, but it's
And
not really
until then you are kind of creating dipoles, and the Ising order is just dipoles, which with
Yes.
capacitors.
So, yeah.
Any other questions?
I thought of that 10 seconds earlier, I was like, so this is a question actually from very early in the talk, where you were talking about the justifiability of neglecting higher bands. Presumably there are some oscillatory phenomena as a function of the length of your ramp that have to do with the ramp acquiring Fourier components that are resonant with the transition to higher bands.
Yes.
Is that effect ever observable?
Not here. I would think it would be difficult, because this is from